So on the first question on the exam, I asked you something that we didn't really talk about in class, and it has to do with material reference frame indifference, or sometimes we call this objectivity, and it has to do with the fact that when we develop a constitutive model, the constitutive model should be invariant to a change in reference frame. Right? If we just simply have some external coordinate system and we do a rigid rotation, then the constitutive model shouldn't change. The stress shouldn't change due to some rigid rotation, right? I mean, the stress is what it is. You deform it. And so then I asked, is the rate of Cauchy stress subjective? And this is important. So there's just something teachable in this we'll talk about for just 1 second here. So if you remember when we talked about plasticity, we used this return algorithm, right? And the way we did that is you have your exam? Huh? Yeah, bring it here real quick. So the reason it's that we're interested in the rate of Cauchy stress is because often in plasticity modeling we use a rate form of the constitutive equations because this makes it convenient to design a return algorithm. Right? This is how we remember in plasticity we have a yield surface, and if we're inside the yield surface we're elastic. If we're outside of it, we're in violation of the constraint conditions, and we have to return ourselves to the yield surface. We're either inside an elastic or directly on it, right? And in that return algorithm, it's often easier to do that in terms of rates. So often we'll develop constitutive models in terms of rates. And so then the question on one was, is the rate of Cauchy stress objective, or does it obey the principle of material reference frame indifference? Okay, so it's actually quite easy to show that it doesn't. You just take the time, So I guess I also said that, a constitutive model is said to be frame indifferent or objective if you can pass it through some rigid rotation and you get the same stress. So then if you just take the time derivative of both sides of this equation, then you get this guy, which is clearly not that, right? And that's it. That's all you have to do. It's not. I mean, that's the answer to problem one. And so there's also a little thought experiment that we could do here. And so let's imagine at time t equals 0, we have a body in a reference frame x and y. And we pull on the body such that we develop some stress sigma xx. So it's just one uniaxial stress. I just pull on it, and I deform it, and I hold it, okay? And I hold it, and I'm not going to strain it anymore, right? I'm just going to hold it at that stress, okay? So still have a coordinate system x and y, and now we're at some intermediate time we'll call t1, and I begin to rotate the body. So I'm holding it at the same stress. Some time passes, and I rotate it such that eventually, sometime t2, I've rotated it 90 degrees, such that what was sigma xx is now sigma yy. So I strained it, and then I just rotated it. Well, clearly the stress is changing via the rigid rotation. So the Cauchy stress is not objective in that sense. Okay? Because remember, the Cauchy stress is an Eulerian thing. It lives in the material reference frame, the deformed frame, right? So what about like a rate of Kirchhoff stress or second Pure Kirchhoff stress, which everything is in the complete reference frame all the time? Then it's going to be, then the rotation, the rate of second Pure Kirchhoff stress would be objective, right? So what do? We often define something called an objective stress rate. A lot of times we'll use this upside down triangle. It is a rate, okay? And we define it as this. And so this, how we choose omega gives us, so if we choose omega to be the W, which is the spin tensor, so remember the velocity gradient can be decomposed into the rate of deformation plus the spin, right? The anti-symmetric part of the velocity gradient. So if it's the spin tensor, then this thing has got a name, and it's called the Yeoman objective rate of Cauchy stress. If we choose it to be R, well, I'm sorry, if you choose omega to be R, where R comes from the polar decomposition of the deformation gradient. So we can take any deformation gradient, we can decompose it into a rigid rotation plus a stretch. So this U is called the right stretch tensor. And there's also an equivalent left stretch tensor and then the same R. I think we talked about this briefly, the so-called polar decomposition. So if we choose R, so we can do this polar decomposition and find R. And then if we use R as a rotation there, then this becomes the so-called Green-Nagdi rate of Cauchy stress. Also, sometimes this is known as the co-rotational rate of Cauchy stress. And if you actually plug, then if you plug this stress rate into that equation, you'll see that in fact this works if you work through the details. So it is objective. And we don't. This is just sort of a little aside. I mean, I don't want to go into all the details. If you ever took a full class in continuum mechanics, you definitely would. There are actually infinitely many objective stress rates. And so just like there are infinitely many stress and strain measures, but the key is that you want to have an energy consistent strain measure to your objective stress rate. And all these stress rates can have problems, particularly the Yeoman rate of Cauchy stress in a state of pure shear. So if you just take a sample and you put it under pure shear, the Yeoman rate will oscillate. And so there are small issues with all of these. The best rate of Cauchy stress, and you get this by the pullback operation of the Kirchhoff stress. It's also related to so-called Lie derivative, this so-called Truesdale rate of Cauchy stress. So the point of this is, and even the point of that question on the test, was just to point out and make you aware, stick it in your mind when you're talking about finite deformations, rotation is important, okay? I mean, when rotation is involved, the first thing you have to do is go to finite deformations to get the correct solution. But then things get harder, because if you're talking about rates, so you have plasticity and you have rate rates of Cauchy stress or other things. Then now you have to deal with objective stress rates. So everything gets more difficult and that's why as we go on in the second half of the class, while I think it's important, we just don't have time to go through all the details and the difficulty of the finite deformation stuff. So from here on, when we do the computations, we're going to use all small strain. Okay, but if you take one thing from this class, remember, if you're solving a mechanics problem and it involves rotations, you have to use a finite deformation theory. Okay. Yep.
So if you do, so this the same equation would be true for strain, right? So E would be R E R transpose. For so if you're saying the stress would be constant for rotation for rigid deformation, the first equation that we're using. So we can do the same thing for epsilon, right? For a strain. So where I want to go is we had an equation for dE dt, which was F d F transpose.
dE dt. So the rate of green Lagrange strain?
Yep.
Okay, yeah.
So it was F d F transpose.
Mm-hmm.
So F is R here, and then if we do that, dE dt would be 0. What is
No. F is not R. F is not R. F is a unique rotation plus a stretch. I mean, not plus, multiplied by a stretch. I mean, these are tensors.
But if R is rigid rotation, like U is kind of pi, isn't that the case?
Yeah. Yeah.
Okay, so when we just have rigid deformation,
Yeah.
and F is equal to R, so that
Then the rate of the
dE dt would
be zero. Yeah. Yeah.
but then if we use E in that equation, in the top equation, E is equal to R E R transpose. If we do the same thing, it would turn out that E wouldn't be objective, but the dE dt would be 0. What does that mean?
No, you don't have to. Yeah, we can discuss it later.
Yeah.
I'm not real sure I understand your question.
Okay,
Yeah. But, yeah. So, yeah, I mean, we won't really do any of this in the class. So, I mean, I just sort of want to make you aware of it. But, yeah, I mean, we'll see how class goes. If we get through everything, I think I'm moving a little faster pace than the last time I taught this course. If we get through everything, maybe we'll look at a finite deformation problem right at the end. But that's not in the plan right now. But maybe, and if so, then we can discuss some of the details of how to do it. Okay. So this slide represents a